Okay, this is another solutions video to help you with a assignment related to AP Classroom, Unit 7, which is torque and rotational motion. This is specifically related to torque and angular acceleration. So we have these graphs that were given to us. The graphs are angular momentum versus time. And so whenever I have graphs, I try to figure out what the slope tells me, what the area tells me. And relative to torque, what do I know? I know that the net torque is equal to I times its angular acceleration. And I also know that the net torque, if it's applied for some period of time, is going to change the angular momentum. This has something to do with time and angular momentum. And if I rearrange that, I see angular momentum over time is equal to net torque. And so sure enough, the slope of these lines is torque, and you can prove that to yourself with respect to units. So I went ahead and calculated all that. What are the slopes? Torque. What are the slopes for each of these sections of lines? Now we read the situation, and we find that we have a disc, we have a torque that's being applied, there is friction, and at 2 seconds, the torque is gone. The external force is gone that's creating that torque, and friction begins to slow it down until it comes to rest. So if I see up here the portion of this graph up to 2 seconds, and this graph up to 2 seconds is when there's an external torque added to the disk, causing an increase in angular momentum, which means that it had to be greater than the torque of friction. Then at 2 seconds, that torque disappears, and that's the frictional force that causes it to slow down and eventually come to rest. So what they want to know is, in the two experiments, which torque is greater, and what about the frictional torque between those two? And if you calculate the slopes, which I did, experiment 1, the applied torque is 10 newtons meters, and in experiment number 2, it's 20 Newton meters. So experiment 2 had a greater torque. And notice the friction in both cases has a slope of -5. In both cases, -5. So I'm assuming the same apparatus. That would make sense if the friction should be the same. So at any rate, you go through here and you find the one that shows that torque 1 is less than torque 2, and the friction is the same amount of torque. So number 2, I have a situation where I have a disc sitting on a axis, a rod that runs through it perpendicular to the paper. We have an unknown radius and an unknown moment of inertia or rotational inertia. Let's see, what are they asking here? Indicate whether the force that's applied to the cylinder and the rotational inertia of the cylinder can be either measured or calculated. And what do we have? I have it highlighted in green. We have a meter stick, a stopwatch, and a force probe. I need force applied, and I need the moment of inertia, I. They told me I couldn't take this disc off of this off of the metal rod, which means I can't put it on a scale. I can't measure its mass. So, but I have a force probe. I can measure the force, so that I can measure directly. And if I have a stopwatch and I have a force probe, I got a meter stick, I can measure R, the radius, and I can find the angular acceleration, right? Because I can say what is kind of what we did in class. We can find delta theta after some time, and we know the initial velocity is 0, and then I can calculate alpha. And once I have the torque, which the force, which will measure directly, and R, which will measure, I can calculate this angular acceleration, which means I can determine I. So essentially, force will be able to be measured directly, and I we're going to have to calculate from measured quantities. All right, this one here is interesting. I like it and I don't like it because anyway, I got this disc again that's a metal rod that runs through the paper, perpendicular to the paper, and R and M, and then I hang a mass B. So they wanted to know how many forces are acting on this disc let's see, how do they call it? How many forces apply to the pulley axle system? Okay, so the axle is part of it. And how many torques? So here is this axle, and this is a side view. And I kind of figured that out after I saw the answers because I was like, what the heck? There's too many forces here. Anyway, so there has to be two strings that hold that axle up. Otherwise, the thing would turn upside down or be a cattywampus. So that's why there's a total of two forces there, FT1, FT2. And then we have force of gravity that's acting on pulling downward from the mass B hanging from it. And we have the actual force of gravity that is acting on the disc. So there's a total of four forces. Now, which one causes torque? Only the mass MB causes torque. Okay. So why is that, by the way? Force of gravity runs straight through the center axis of rotation, and FT1 and FT2 are not on the disc that is capable of rotating, so it's not actually causing a torque. Okay. All right, next. Which of the following graphs, excuse me, if any, shows the angular velocity omega of a pulley as a function of time after the block is released? Oh, I think this is related to the same question. So we started from rest. This we know for a fact. It started from rest. Tell us that. Release from rest. We know that it's going to accelerate, so acceleration cannot be equal to 0. I don't know what that is. That should be cannot equal 0. Okay, because it's going to start from 0 and start speeding up because I'm adding a net torque. So here's what I know. Slope is of this graph, what they told me, is equal to its angular acceleration. And also know the area is equal to its change in angular displacement. So let's look at all the options. A cannot be correct. Excuse me. Because the initial angular velocity does not equal 0 in this graph, so that can't be correct. Plus the slope is equal to 0. We know the slope has to be something other than 0. B, the initial angular velocity is 0 and the slope is constant, which is great because acceleration should be constant. That is the answer, but let's go look at C. Slope is not constant, and we should have a constant slope because the acceleration is constant because the torque is constant. So that is why C is wrong. D is wrong because the initial velocity is not 0. So that's B. Now we're asked to determine the change in angular momentum of that disk. Okay, what is the change in angular momentum if it's released from rest until some time t naught? Well, again, change in angular momentum, something to do with that torque and time is the impulse equation relative to rotational world variables. And so if I want to know change in angular momentum, I've been given the time t0. Now I just need the torque. The torque is the mass B times little g, which is the force that's putting downward on the disk at some distance r. And so there you go. And don't forget it's mb, little mb, because that's the one that's hanging. Okay. Number 6, I have a disk of radius 0.2 meters, rotates about its center with an angular velocity of 50 radians per second. The disk is placed in contact with the wall. If you kind of can see that over here, I drew it. I have an initial velocity of angular velocity of 50 radians per second. I'm going to have some friction that the wall creates, and then it's going to come to rest. So they want to know what is the linear impulse that is analogous or similar to the one that we just described. What is impulse? Impulse is the force times time equals the change in momentum. So if we look at A, they tell me a block is initially at rest. Well, we didn't start from rest. We started with some angular velocity. So that's no good. B, same thing. See, it's initially traveling at 10 meters per second, and then somebody applies a force, and it's applies a force in the direction of the velocity. That's going to increase the velocity. So that's not what happened here. We applied a frictional force in the opposite direction so that we came to a stop. So that would be why answer's D. So it's just kind of making sure you kind of start to see the connection. This is all the same thing, except in rotational world. All right, here's a situation where I have a string that's attached to a pulley of known rotational inertia. So I know this value, I sub P. I want to determine the relationship between torque and the change in angular velocity if I put some force on that disk for 2 seconds. So I know IP. So I know that the net torque equals the rotational inertia, which I have, times alpha. Okay, what is the definition of angular acceleration? Change in angular velocity versus time, or over time. And so I'm looking at all of the things that I need in order to determine the relationship between torque and angular change in angular velocity. I don't need the mass of the pulley because I have the rotational inertia already, but I need the radius because I got to know how much torque is put on there, and I need the force. And if I have a stopwatch, which I have, I can calculate again using similar to what we did in class, where I start initial equals 0, and then I have some time I can calculate, and then I can find delta theta at that time, and then I can know everything. I can know angle, final velocity, and I could also determine its angular acceleration. So B and D. Number 8, I have this disk that's traveling at some velocity, angular velocity, called omega naught. And then another disk falls down on top of it, and this angular velocity is 0. And they're going to stick together. And when they do, it'll have something that looks like this. And this will be, I'll call disk XY. And guess what? It will have an angular velocity that's smaller. Okay. And why is that? Because the initial angular momentum of Y plus the initial angular momentum of X, which happens to be 0, will equal the final angular momentum of the object XY. This is very similar to what we did in linear land. So I have, they want to know which description is analogous or similar to what we just described above. And so if you can imagine the block X traveling towards block Y has no velocity, they stick together. Now that velocity, final velocity, XY final, does not equal the initial velocity of X, because this velocity will be less because the momentum's conserved, therefore the velocity will be decreased because the mass of the system is now increased. And so if you go through and read that, you'll find that B is correct, because notice they give you a different velocity as opposed to A, which tells me the same original velocity, and that can't be the case. It's got to be something different. Number 9, I have a graph, angular velocity versus time. Slope is equal to acceleration. Area is equal to change in angular position. We have a situation where a student makes a statement, and the student's statement says that a net torque is exerted on the rod because the rod's angular momentum is increased. Well, the velocity is increasing, which if the mass is the same, which it is, then that means the momentum is increasing. Well, if you see that you have a slope of some positive number, in order for me to have acceleration, I have to have a net torque. And I'm just looking at all the relationships here. So yes, because the angular velocity increases with time, angular momentum of the rod increases with time, which it does. It can only happen if I have a net torque. B is interesting. I'll tell you, read this for a minute. Yes, the area is positive. Yes, delta theta is increasing. However, you can have a change in delta position when you have zero net torque. You can have a situation where you have no friction and you have a constant angular velocity, and you will have a change in theta. So B is incorrect. Okay, and C and D I think are a little bit more self-explanatory. I believe that is it.